few introductory slides just to introduce to all of you our conservation center. So the full name of the Conservation Center in Venaria is Centro per la Conservazione e Restauro dei Beni Culturali, la Venaria Reale. We are one of the 3 national strategic poles for the conservation, research, study, and higher education on cultural heritage. You may be more familiar with the other 2 traditional conservation centers in Florence, the Opificio delle Pietre Dure, and in Rome, the Istituto Superiore per la Conservazione e Restauro dei Beni Culturali, that were founded in the 30s and in the 60s. We are located in a beautiful location, as you've seen before, in the former stables, horse riding tracks, and dog shelters of the Royal Palace of Venaria, which is a former royal residence of the House of Savoy, and actually a beautiful masterpiece of Baroque architecture. We are located just outside of Turin, in the region of Piedmont, in the northwest of Italy. The CCR is a no-profit foundation that was founded in 2005, 18 years ago, as part of what is still called the largest conservation project in the whole history of Europe, which involved not only the Reggia di Venaria, but also the gardens and the town's historic center. The architectural complex has been for quite a while a UNESCO World Heritage Site. It has reopened to the public back in 2007 after this huge conservation project was completed. And you can purchase a ticket and visit the Royal Palace, the gardens, and also the temporary exhibition space that is hosted inside the Reggia di Venaria. So the CCR was founded by both public and private institutions, and that gives us a lot of flexibility in terms of activities that we carry out on a regular basis. We are a very interdisciplinary team of people that includes scientists, conservators, and art historians as well. So we basically follow the works of art in their entire life cycle, from the examination, monitoring, and study of the works when they come to our conservation center for conservation treatments. We do also research, study, and technology, and this is actually what I'm going to be focusing on today. We take care of the prevention, maintenance, conservation, and management as well of the works of art. And we are very active in the outreach, dissemination, and training activities. And this is a very important aspect for us, and I'll show you why in just a second. So one of the many souls of our conservation center in Venaria is obviously the conservation laboratories. We currently host 9 conservation laboratories that are specializing in the treatment of various types of cultural heritage materials and artifacts. So we have paintings on canvas and wooden panel, wooden sculpture and furniture. We have stone materials, wall paintings, and architectural decorated surfaces, textiles, tapestries, carpets, leather, and ethnographic materials. We have glass, metal, and ceramic artifacts, contemporary art, as well as works on paper, parchment, and photographic supports. Besides the conservation laboratories, we also have fully equipped scientific laboratories that are active on different fronts, from the scientific analysis of the works that come to our conservation center for treatment, to advanced applied research projects that we usually carry out in collaboration with outside academic institutions, like, for example, the University of Turin and other universities all over Italy, through grant-based national and international projects. So usually when a work of art comes to our laboratories for treatment, there's a specific path that goes through different steps, in a cycle that usually begins with photographic and multiband imaging documentation and scientific analysis that's going to guide and inform the conservation treatments. So usually each scientific and technical study that we carry out is tailored to the questions that are raised by the conservators, the curators, the art historians, and other museum professionals. And it's a process that involves many steps. So we usually begin with what we call non-invasive analysis. Some of you may be familiar with this terminology. By non-invasive, we mean a scientific method that can be applied through instrumentation that can be placed in front of an object, but there's no physical contact between the machine that we are using and the object that we are studying. Obviously, this has the great advantage that we don't need to remove microscopic samples from the artwork that we are studying. But it also comes with its own set of challenges because the type of information that we can provide using this methodology can be limited at times. So depending on the questions, we can also take another step and remove a selected number of samples from the object, and then we analyze these samples through a minimally invasive or micro-invasive techniques. I indicated here some of the instrumentation and analytical techniques that we have at our disposal in the scientific laboratories at the CCR, which include multiband imaging, three-dimensional imaging, radiography and tomography, optical microscopy, and several spectroscopic techniques, so techniques that use different wavelengths of light to provide chemical information on the objects that we are studying. And we also carry out biological investigations as well. One strategic area in our conservation center is preventive conservation. This is very much an interdisciplinary area that involves scientists, curators, art historians, and conservators as well. Our goal is to define and deliver systematic actions and integrated activities aiming to develop and formulate strategies for the best preservation of our cultural heritage for future generations. And usually, the strategies that we formulate are tailored to the specific needs, requirements, and conditions of each site where we are active in. So by systematic actions, I mean, for example, the scheduled maintenance of the works of art, microclimate studies with the monitoring of certain environmental parameters, like, for example, the temperature and relative humidity, integrated pest management, so the study and control of different types of pests, so organisms that can pose a risk to the cultural heritage, and materials testing, so the chemical analysis of all those materials, starting from the display cases in museum galleries, for example, that come into contact with the materials of the works, and that we must be aware of. Some examples of target sites that we operate in include obviously the Reggia di Venaria. They're our neighbors. This is not the only royal palace in Piedmont, obviously. There's a whole bunch of historical residences that used to belong to the House of Savoy and where we are doing environmental monitoring and just a series of integrated activities in the field of preventive conservation. We are very active in museums and churches on a national scale as well. The CCR is the headquarters of a master's degree, a 5-year master's degree in conservation and restoration of cultural heritage coordinated by the University of Turin, which brings to us a total of 100 to 120 students per year. That's a great resource for us to have these students working in our conservation and scientific laboratories. There are many strengths to the master's degree, including, for example, a combination between theoretical lessons with practical activities that the students carry out in our laboratories and on-site work as well. There's a very convenient and favorable professor-to-student ratio of 1:5. We provide advanced training in 5 professional fields for conservation, and the students achieve the professional qualification of conservator according to the Italian laws. It's a very much interdisciplinary master's degree that combines technical, scientific, and humanistic disciplines. The third soul of our conservation center in Venaria is what we call in Italian the Scuola di Alta Formazione, SAF, Advanced Training and Study School, whose mission is to provide high education at different levels by organizing classes, courses, seminars, and schools. What I indicated at the bottom of the slide to the right is a wonderful project that we launched in September of last year, 2022, which is a digital platform that we call CCR Digital Lab, and I invite you all to check out the link at the bottom of the slide, where you can find different online courses, seminars, and educational offers that are addressed to students, professionals, different professionals actually in the field of study and research of cultural heritage. All right, so this is the outline of my presentation today. Unfortunately, I'm not going to be talking about musical instruments because that's just not my area of expertise, but I'm hoping to be able to share a series of relevant case studies and experiences in the field of science for cultural heritage. So I'm going to undertake a travel back in time, so starting from contemporary art with the case study about a technical investigation of the materials and techniques of contemporary artist Carmen Herrera that I carried out when I was working at the Metropolitan Museum of Art. And then we're going to switch gears and go back to Greek and Roman times with three case studies about technical investigations that we carried out in the archaeological park of Herculaneum, Pompeii, and also a similar work that we carried out at the Met as well. So the main goal of these case studies and my whole presentation today is hopefully to be able to demonstrate the multifaceted role of science in the study and research of cultural heritage. So let's begin with the first case study. So this is a big project that I carried out between 2015 and 2016 when I was an associate research scientist at the Met in the Department of Scientific Research. So Carmen Herrera is a wonderful contemporary artist that was born in Cuba in 1915, and she just recently died in February of 2022 last year in New York. She reached international fame very late in her life and career, and she had the first exhibition featuring her work when she was 89 years old. Just to give you a little bit of context, the framework in which this project was carried out was the Network Initiative for Conservation Science, or NICS, which was a pilot program that was launched by the Department of Scientific Research at the Met in September of 2016, thanks to financial support for the initial 6 years from the Andrew W. Mellon Foundation. And they just recently got an additional grant for another 3 years that's going to cover them until 2024 from the Sloan Foundation. The main goal of the Network Initiative for Conservation Science is to provide scientific support for a core group of partner institutions in New York City, from the American Museum of Natural History, MoMA, Guggenheim, the Morgan Library, and so on. These are all institutions that don't have scientists on their staff or scientific equipment or laboratories where they can analyze objects in their collection. So this is a great resource for all of these institutions. So basically what happened is that a conservator from the Whitney Museum of American Art reached out to us back in 2015 with a request to analyze a group of 8 paintings by Carmen Herrera that were going to be featured in the first retrospective exhibition organized by the Whitney Museum that was going to take place between September 2016 and January 2017. So Carmen Herrera was still alive at the time, and she was helping the curators to set up and organize the exhibition. And the curators thought there was something strange when they realized that the labels of some of the paintings from the late 40s and beginning of the 50s were reporting acrylic-based paints as the medium allegedly used by Carmen Herrera during a specific time in her artistic production when she was working in Paris, so between 1948 and 1953. So this sounded a little strange to the curators organizing this exhibition because the known date of introduction of acrylic-based artist paints to the European market was 1963, so at least a decade later to the date of these paintings. They went under the name of Cryla, and they were produced by a company led by George Rowney and Sons. So again, because this information sounded strange, the curators wanted to have scientific confirmation of the chemical composition of Carmen Herrera's paints. So we carried out a study with the first goal to identify the binding media in a group of paintings from Herrera's Paris period, so 1948 to 1953. And then because this is contemporary art and this is an artist that nobody ever studied before, we were also interested in knowing her materials, techniques, and studio practice. So that was the second phase of our scientific investigation. This is the 8 paintings that our study focused on. So again, spanning a time span from 1948 to 1953. In the first phase of the scientific study, we mostly use microinvasive techniques, in particular 2 techniques called FTIR spectroscopy and pyrolysis gas chromatography mass spectrometry. I'm not going to go into details into these chemical methods, All you need to know is that they're specifically suitable for the analysis of organic materials and organic binding media in general. This is what some of our data look like. So again, I'm not going to go into detail into explaining all these complex spectra and graphs, chromatograms. But what this data told us is that a first group of paintings, actually spanning the entire time that we were considering, 48 to 53, appeared to be based on oil paints. We also noticed, and that was the interesting part, that there seemed to be a progressive introduction starting from the late 40s into the early 50s of different types of media as well, including, for example, alkyd paints, polyvinyl acetate, and acrylic-based paints as well. So what we were able to say is that Carmen Herrera did pioneer the use of acrylic paints in Europe in the late 1940s, which was a very important information for us because it really contributed to rewriting the history of the use and availability of certain types of novel materials back in the late 40s, when the use of this material was not known to this current day. So the second phase of our study used both non-invasive and micro-invasive techniques. You can see some images of our analysis that we carried out in the Whitney laboratories and in the Met laboratories as well. Again, I'm just going to give you some highlights in terms of results that we were able to get using the different analytical techniques. So this is a combination of what we call multi-band imaging techniques that you may be familiar with. So one discovery that we made was that Carmen Herrera used an underdrawing and pencil notes that you can see here traced with red that likely indicated the geometric and chromatic schemes that she intended to apply to her paintings. So there was a careful preparation to the painting composition. We used some point and also scanning X-ray-based technique to figure out the range of elements, chemical elements that were present in the materials of the painting. So for example, in this case, we analyzed red, orange, and black areas, and we found elements such as cadmium, selenium, sulfur, zinc, calcium, and titanium that spoke to the color palette that she was using. Using a scanning XRF, so X-ray fluorescence technique, we were also able to map the distribution of these elements that we found using spot analysis. So that again gave us information on where exactly on the painting these pigments were used. And because this was a very complex study with very complex questions, we decided that it was necessary to remove some microscopic samples, and this is a step that we always take through a close collaboration with the conservators, selecting together the ideal spots for sample removal. And these are just some optical microscope images under visible and ultraviolet light that basically show us a complex stratigraphy. So basically, the white layer that you see at the bottom is the preparatory layer. And then on top of the preparatory layer, there are many, definitely more than one, paint layers. So usually a first black layer that is overpainted with red in some cases or with yellow and orange in some other cases. So obviously we don't have a time machine and we'll never know if this was intentional or not. All that we can say is that definitely Carmen Herrera's creative process seemed to develop through subsequent compositions. So she first painted her canvas black, and then either she applied other colors on top to convey a certain tonal effect on the surface, or maybe she just changed her mind and then she overpainted the black with the red and the yellow and orange pigments. This is a similar information to what we saw before, but on a micro scale. So this is information obtained with a very powerful microscope called a scanning electron microscope that can combine morphological information on the aspect of the pigments that were used by Herrera with information on the elements contained in that particular spot that we are analyzing. And again, we combine these elemental techniques with vibrational techniques like Raman spectroscopy Again, without going into detail, you just need to know that this is a technique that can give us a fingerprint of the molecules and chemical compounds that are contained in the pigment mixture. So just by looking at the Raman spectra, we were able to conclusively identify all the pigments. So through this combination of analytical techniques, we were able to figure out that she was using a preparatory layer based on titanium white, a particular form of titanium white called rutile, anhydrite, and talc. And then her paint layers contained a fairly limited color palette, including, for example, many types of blue, from Prussian blue to cobalt blue, cerulean blue, ultramarine blue, iron earths, cadmium pigments, and so on. We also did scientific analysis in support of a conservation treatment for the painting that I just showed you, Iberic. We noticed through microscopic observations presence of a grayish dirt layer on the surface that you can observe in these two micrographs. And PyGCMS analysis revealed the presence of a thick layer of nicotine. And that matched some information that we had about Carmen Herrera, who was said to be a heavy smoker and painting her paintings in her studio while she was smoking. So that actually made perfect sense. And thanks to this information that we were able to provide, the conservator, Isabelle Duvernois at the Metropolitan Museum, who carried out the treatment, was able to tailor the treatment using a particular methodology called a modular aqueous system, which is just a fancy way to say saliva, to clean the painting. And I report here a comparison of what the painting looked like before and after the cleaning. So this study also had significant implications in terms of painting acquisition and exhibition as well. So Tony Beccara, who was one of the people who were involved in the study, was Carmen Herrera's friend and manager, decided to donate this painting that you see here, Iberic, dated to 1948, to the Metropolitan Museum, also in recognition of the scientific findings. The painting was featured in a wonderful exhibition, I should say a milestone exhibition, that was held at the museum actually during the pandemic, Making the Met from 1870 to 2020, which was organized by the museum on the occasion of the 150th anniversary. We were very active also in terms of dissemination of research findings. So we published a couple of scientific papers, and I report here the exact bibliographic references just in case anyone is interested in learning more about the results of our study. We were featured on the art newspaper about the NICS program and specifically about our discoveries on Carmen Herrera. And thanks to the collaboration of many colleagues at the museum, we were also featured on the museum's social media. Okay, so let's go back in time. And my next case study is actually a smaller project that we carried out in Herculaneum just last year. I'm going to give you a little bit of context here as well. What we were requested to do was just a phase of scientific investigation that was contextualized in a much bigger project, which I'm sure you are all familiar with, which is the Herculaneum Conservation Project, which was sponsored by the Packard Humanities Institute and the Soprintendenza Speciale per Pompei, Ercolano e Stabia. This is not the time or venue to go into details about that project, but I reported the link here, so you're welcome to check it out if you want to hear more about this project. So, obviously, we're talking about the 79 AD Vesuvius eruption, following which there was a collapse of 250 wooden fragments from the polychrome wooden ceiling of the House of the Telephos relief that were found during an excavation that took place between 2009 and 2010, covering an area of about 55 meters on the ancient shoreline. Thanks to the particular conditions of the volcanic burial, the wood was actually perfectly preserved and not carbonized, uncharred. And in the following years, that prompted several studies in different fields related to this finding, from studies on Roman woodwork carpentry to roof construction techniques, wood identification and dating, as well as a preliminary characterization of the decoration technique. So between 2017 and 2019, the conservators at the Archaeological Park of Herculaneum decided to carry out a consolidation treatment of the soaked polychrome wood using a mixture of hydrogenated sugars dissolved in water at different concentrations. And then after this first phase of consolidation, they tested different cleaning methods, including laser cleaning and just the more traditional chemical cleaning, trying to remove the superficial excavation soil. They figured out that laser cleaning was probably the most effective and selective methodologies for this purpose. And again, here you can see the difference between what this fragment looked like before the cleaning and after the cleaning. So I guess a pretty significant result. So we got a call from the conservatory in Herculaneum asking us to carry out a technical study of the remnants of the original polychromy of some of these wooden fragments that was revealed by laser cleaning in 17 fragments of the ceiling of the House of the Telephos relief. And these are the 17, it's the body of the 17 fragments that we considered in our technical study. So the analytical protocol that we developed in this case was just a result of some of the requests of the conservators in Herculaneum, who asked specifically for a completely in situ and non-invasive technical study. So that was one of the first challenges that we encountered, because obviously, as we've seen before, non-invasive analysis can obviously have the great advantage of not needing to remove samples, but it can also provide us pretty limited information in some cases. And another challenge was represented by the presence of residues from the burial environment that were still found on the surface of certain fragments despite the cleaning. So we used a combination of non-invasive techniques, starting from photographic and multiband imaging techniques, going through point and scanning XRF analysis, as well as Raman spectroscopy with 2 laser excitations. So I'm just gonna go through the most relevant results by color. So for white color fields, we found 3 types of white pigments, one based on calcium with traces of titanium, one based on lead with traces of vanadium that we found, according to the literature, to be compatible with the Vesuvian mineralogy, and a color field that was apparently based on zinc, and that indicated a possible modern repainting since zinc white was introduced in the 19th century. We also detected with Raman spectroscopy a pretty specific mineral called wolfenite, which is a lead molybdate that is typical of the mineral ore of lead deposits, where it is usually associated also with other minerals. And that was a very specific finding. We digged in the literature a little bit, and we actually found that molybdenum as well as vanadium were 2 elements that seemed to be actually present in the Vesuvian mineralogy. Red colors were mostly based on red ochres that we identified through elemental mapping with the scanning XRF and vibrational analysis with Raman spectroscopy. In some cases, I don't know if you can see the cursor on the screen, probably not, but if you look at the fragment on the right, we also detected a distribution of iron in certain areas where no traces of red pigment were actually visible. So through some of our analytical technique, we were able to highlight the presence of pigments that are no longer visible under normal lighting conditions. Blue color were mostly based on the presence of Egyptian blue. Again, there are specific analytical techniques like infrared-induced visible luminescence that are specifically tailored and suitable to highlight the presence of these pigments through their physicochemical properties, like in this case, luminescence, even in cases when no visible traces of pigment are found on the surface. This information matched information that we got from the scanning XRF with the detection of copper and calcium. We're talking about a copper and calcium silicate, so that makes sense. And in some cases, if you look on the right, fragment 193, we're also able to highlight the presence of some decorative motifs that are no longer visible on the surface, mostly due to a severe degradation of the wood. Black colors were found to be based on a carbon-based pigment. In some cases, like for fragment 56 that you see here, we actually got very strong responses both with infrared light and with the VIL technique. So if you look at the first image on top, that's the infrared reflectography of these fragments. You can see that the polychrome part in the center of the fragment has a very strong black response. So that usually indicates the possible presence of carbon-based pigments. And again, you can probably see, even if it's very small, in the upper part of the fragment, a beautiful kind of round or wavy decoration that is actually no longer visible if you look at the visible image of the fragment. So a contextual response that we got with the VIL technique is a very bright response that indicates the presence of Egyptian blue. So what this combined information tells us is that probably some of the color fields that today appear as dark or black were actually produced by overlaying a first preparatory layer that was black, so made with carbon black or a carbon-based pigment, and an overpainting with Egyptian blue. And that actually is obviously a very known technique for Roman wall paintings as well. In some cases, we noticed that some of the fragments with areas that clearly appear dark or black have a very strong black response in the IR reflectography, but no response in the VIL image at the bottom. So that actually indicates the presence of true black color fields that were produced with a carbon-based pigment. And what the infrared reflectography also told us was that the same carbon-based pigment was also used in some cases to draw some of the outlines of certain shapes in some of the fragments that we analyzed. So the combined information from the technical and archaeological study was very useful to put forward a first hypothesis in terms of reconstruction of the polychromy of the ceiling. Obviously, again, we don't have a time machine, so we will never know that this is 100% accurate, but at least it's an approximation of what the ceiling might have looked like when it was first painted. So very useful information. And for those of you who are interested in taking a look at the wooden fragments, there is a wonderful exhibition called Materia, the wood that didn't burn in Herculaneum, which is going to be up until December of this year at the Reggia di Portici, the Royal Palace of Portici, which is very close to Herculaneum. And I also indicated to the right some of the literature that was published as a result of this study. This is just, it's not meant to be comprehensive or complete in any way, but I think it's a good starting point to start learning more about this wonderful collaboration. I'm going to go through this case study very quickly because actually this is something that my colleagues Elena Basso and Federico Carò, two geologists, carried out in the past 2 years, I guess, at the Metropolitan Museum of Art, with a very similar aim and scope compared to the Herculaneum project that I just spoke about. So the aim of this study was actually a technical investigation of the extant and original polychromy in a body of ancient sculptures in the Met's Greek and Roman collection. This is just one of the sculptures that were the object of this technical study. It's an Attic funerary stele with a sphinx that used to be polychrome, and actually, if you look at the right, you can see a beautiful color reconstruction that was already made by an archaeologist, if I'm not mistaken, in 1944, which turned out to be pretty accurate and matching the information from our technical study. The analytical protocol involved both non-invasive and micro-invasive techniques in this case. There were pretty great challenges that my colleagues had to go through to complete this technical study because this sculpture was enclosed in a display case in the Met Galleries, and it could not be moved away from there. So as you can see in these images, all the technical analysis, examination of the surface through portable stereo microscopes and so on, had to be carried out just by opening one side of the display case and inserting the instrumentation or locating the instrumentation in front of the Sphinx. In this case as well, just like for the Herculaneum fragments, there was the presence of a thick crust from the burial environment, which made data interpretation a little bit challenging. And obviously, in this case as well, my colleagues had to minimize sampling and sample size, which is something actually very frequent in this type of technical studies. So I'm not going to go into details because many of the techniques that they used are actually the same techniques that we used in Herculaneum. But again, In this case as well, my colleagues basically used the combination of analytical techniques that provided information. It's like putting together different pieces of a puzzle. So in this case, they were able to detect some elements like copper and mercury on some areas of the wings of the Sphinx, for example. They were able to map the distribution of the pigments on the wings, on the diadem, on the hair, on the chest, the back, and the tail. They were able to visualize elements and pigments in particular, like Egyptian blue, which we are all very familiar with by now, that were no longer visible on the surface under normal visible light conditions. They found two different breads being used on the Sphinx, so an iron-containing earth, cinnabar, as well as two different copper-containing blues, which were Egyptian blue and azurite as well. One interesting implication of this study was that in this case, the detection of traces of a particular element, arsenic, in the iron-containing pigments gave them information on the possible provenance of some of the pigments. So they checked the literature, and this particular pigment used on the Sphinx seemed to be traceable to the island of Kos in Greece, to a particular workshop. So that was very interesting information. And in this case as well, based on the results of the technical study, they were able to produce a colored reconstruction of the Sphinx that actually, as I told you before, overall matches the 1940 reconstruction by the archaeologist. And both the original sculptures and the color reconstruction were actually featured in this exhibition, Chroma, Ancient Sculpture in Color, that just closed down in March of 2023. The museum also produced an augmented reality app that you're welcome to access just by scanning this QR code. And to the right, this is just me having some fun and locating the recolored Sphinx in my living room in Torino. So you're welcome to give it a try if you want to have some fun as well. All right, so this is the last case study that I'm going to talk about today. This is all work that was conducted at the Conservation Center or by my Conservation Center colleagues before my arrival. It's actually a very nice collaboration, was undertaken among the CCR in Venaria, Reale, the University of Turin, and the Archaeological Park in Pompeii since 2016. The two main areas of this collaboration were on training and research activities. In terms of types of artifacts, we actually focused on various types of artifacts, from mural paintings to glass, metal, and ceramic objects. And we also carried out a comprehensive technical and archaeological study involving the House of the Ancient Hunt in Pompeii. And this latter case study is what I'm going to be talking about in these last few slides. So as I just said, this was an integrated technical and archaeological study. So from the scientific point of view, we focused on different aspects that needed consideration in the House of the Ancient Hunt. So a first study of the materials and techniques of the mural paintings and the mortars that were used in the house. We did a study of the state of preservation of the surfaces, focusing our attention, for example, on certain degradation processes, for example, the formation of soluble salts and the presence of biodeteriogenic agents. The house was subjected to a number of past conservation treatments, so we also studied the materials from these conservation treatments that happened before our intervention. We then evaluated with scientific analysis and testing the effectiveness of the conservation treatments that we delivered. And we also carried out a microclimate study involving, for example, the monitoring of the environmental parameters. All right, so starting from the technical study of the materials and techniques of some of the beautiful wall paintings in this house, just like we've seen before for the Herculaneum case study, for example, you can see in the visible light images at the top that some of the features and compositional elements of these wall paintings are no longer visible under normal visible diffuse lighting conditions. So we use the combination of multi-band imaging techniques and X-ray based techniques to be able to highlight the presence of some of the architectural structures. For example, over here, the outside garden of the house that is depicted in the wall painting. We were able to highlight the presence of pigments that are no longer visible with our naked eye, like Egyptian blue with the VIL technique over there in the center. And we were able to map the presence of pigments, elements that were used to trace back the presence of certain pigments, outlining a beautiful deer in certain areas of that wall painting at the center. This is another wall painting that was found in the tablinum in room 11 of the house. And obviously the first thing that comes to our eye is the presence between 1.4 and 1.7 meter of a pretty evident green coloration of the surface of the wall. So the question was, is this green color that we observe today the result of some degradation process involving the blue pigment that was applied at the bottom and the top, or the result of some other degradation phenomenon? So in this case, we needed to remove a microscopic specimen just to figure out the painting technique of this particular wall. You can see here the scanning electron microscope image and the visible optical microscopy image to the right. So those two images combined were very useful to provide information on the painting technique, because what we see there is the presence of a first layer of a carbonatic plaster with calcite and dolomite inclusions, what we call in Italian intonachino. Over this first layer, a second green layer made of green earth was applied, and that was overpainted with an Egyptian blue layer. So we actually figured out that this particular fresco painting was actually realized by the application of a green preparatory layer. So the green that you see here is just the result of a surface degradation exposing the preparatory layer. We were also able to discern the dimension of the grain size of some of the pigments used that obviously also affect the final tone and coloration that you observe on the surface. And we were able to highlight the presence of some other degradation processes, like the presence of gypsum very close to the exposed surface, which indicated a particular type of degradation of the carbonatic component due to the presence of pollutants in the atmosphere and humidity as well. We studied the mortars, so this is a particular example regarding a detached plaster fragment that we found on the ground outside room 12. And to the right, you just see the cross-section, which highlighted the presence of the three usual layers, so an arriccio preparation, an intonaco plaster layer, and the coccio pesto finish, which matches very well the technical literature on Pompeii mortars. So other information that we were able to provide starting from this study was the use of pozzolanic mortars based on aggregates of volcanic origin that are traced to the Somma Vesuvius area, so the use of local materials, which is consistent with the literature about other Roman sites as well. We also detected an ongoing biological degradation phenomenon with the penetration of what we call the fungal hyphae down to 1.5 to 2 millimeters, which was causing the disgregation of the material itself. Speaking again about pigment degradation, this is a very well-known phenomenon in Pompeii, where there is in many mural paintings a color change from yellow to red that was caused by the transformation of the yellow ochre pigment into hematite, so iron oxide, by loss of the water molecules as a result of strong heating above 250 degrees Celsius. And there was probably also a partial accumulation of ash and pyroclastic materials at the bottom of the room that may have protected the lower portion of the wall, causing an increasing temperature gradient going from the bottom to upper portions of this wall. We also focused on the state of preservation of the surfaces. So one phenomenon that we were able to study was the formation of what we call soluble salts on restoration mortars. In this case, for example, this is just an example of, say, the degradation product that we were able to detect that's called anhydrous sodium sulfate. Overall, in the study, we were able to detect many different anions, from sulfate to nitrates, oxalates, chlorides, and fluorides, and many counterions as well, speaking to different degradation phenomena. We also have a natural science and biology expert on our team, which together with colleagues from the University of Turin was able to carry out a thorough study of the biodeterioration processes. So when I say biodeterioration, I actually mean the colonization of biodeteriogenic microorganisms that were found both on covered surfaces and also in areas that are exposed to weather conditions. She identified many different species from unicellular green algae to cyanobacteria, lichens, mosses, and fungi as well. And that was very important information to develop ad hoc biocide treatments. We also studied, as I mentioned earlier, materials from past conservation treatments. So this was just a representative example of a black pigment applied on a mural painting in room 15. Where you can clearly see, I believe, in these two images at the left, particular translucent characteristic to the surface. That was because an acrylic resin, paraloid, was applied to the surface, so that was clearly a conservation material applied within a previous conservation intervention. We detected many materials from past interventions, including acrylic resins, but also synthetic resins of different types, like, for example, polyvinyl acetate, as well as restoration mortars. So after the first phase of technical and scientific investigation, our conservators carried out different conservation treatments. Some happened on site. And what you see here is our students of the third and fourth year of the master's degree in conservation and restoration of cultural heritage who are working in the house of the ancient hunt. They are required to perform a 150-hour curricular training, which obviously happens under the careful supervision of the teaching staff and conservators from our conservation center. Some of the artifacts were also brought back to the conservation center for laboratory treatments that happened in our laboratories of stone materials and glass, metal, and ceramic artifacts. From a scientific point of view, some of our colleagues also carried out in situ evaluations of the effectiveness of the conservation treatments done by the conservators. So over here you see two of our colleagues performing water absorption tests, colorimetric measurements, and video microscopy examinations that just to check and evaluate the surfaces that underwent cleaning and consolidation processes. And we also did, as I mentioned earlier, a careful microclimate study that involved the use of data loggers that you see in these two pictures over here. There are devices that are used to monitor environmental parameters like the temperature and relative humidity in different types of rooms. So open rooms, semi-confined rooms, and confined rooms, also to see the different effect of the environmental conditions in different types of environment. We also use infrared cameras and thermometers, as well as contact hygrometers for thermal investigation, so with the goal of producing a thermal map that can give information on the changes of temperature between one area and the other one. So the overall aim of this environmental study was to highlight and point out possible critical conditions that may activate or promote materials degradation, including, for example, the presence and migration of the water in the material's porous structure. And obviously, the final goal is to devise and formulate suitable strategies for the best preservation of these rooms for the visitors and for future generations as well. All this information was included in a great exhibition that was held at the Conservation Center in Venaria in the winter of 2018 called Pompeiana Fragmenta, which was curated by our colleague archaeologists from the University of Turin, Diego Elia and Valeria Meirano. All right, so I think I've come close to the end of my presentation. I just prepared a couple of slides to kind of summarize what I tried to convey to you this morning through the presentation of these 4 case studies. So what is the role of science in the study of cultural heritage? First of all, we can provide information and enhance the current scholarship on the artist's materials and technique, and provide information as well on the pioneering use of novel materials, like we've seen in the case of Carmen Herrera. We can gather information on the authenticity and attribution of certain works of art to certain artists or cultures. We can shed light on cultures, practices, and trade routes, for example, by highlighting materials and techniques that are native to a certain geographical area. One aspect that we've seen, again, with Carmen Herrera is very important is the relationship with living contemporary artists that can help us enhance our understanding of their work, their studio practice, and then we can use a systematic technical study to actually corroborate their memories. We can perform an evaluation of the stability and degradation phenomena that sometimes occur in our works, included but not limited to fading pigments, deteriorating plastics, outdoor stone and metal sculptures. We can propose an approximation of the original appearance of the artifacts, including, as we've seen, cases of lost polychromy, through the ultra-sensitive detection of materials or traces of materials that are currently invisible to the naked eye. We can also use science to guide and inform conservation treatments and the development of strategies for the best preservation of the cultural heritage for future generations. And we've done work as well to support acquisitions and exhibitions in museums and to promote and enhance the fruition of our cultural heritage by the public. And these are my 2 cents, some things that I learned just working in this wonderful field of science applied to the study of cultural heritage. So what I call the key elements to the success and actual usefulness of science. So first of all, a close collaboration of the scientists together with the other professionals that are active in the cultural heritage field, so conservators, art historians, and curators. And that can be really key, starting from the steps of identifying suitable areas for analysis and for the removal of samples, and also to contextualize and get right the interpretation of the results that we get with scientific analysis. We do a lot of applied work in our laboratory where we just basically apply technical methodologies of analysis to our works. But another aspect that I think is very important is the ability to conduct research-driven work, which is actually what can advance the science and technology that is used in this field. It can help us expand the available databases that we use for comparison studies, and it can also constantly improve the current applicability of the analytical techniques. The aspect of dissemination, I think, is also very important. Dissemination of the research findings to an audience of specialists and experts, which can pave the way for future work on the same topics, and it can help us share the benefits of our study, and it can encourage collaboration among experts. And outreach to the general public is also a very interesting aspect to be considered, because it can raise awareness, it can draw the stakeholders' attention, it can help attract funding, maximize social, political, and economical impact of our studies, and foster policy change based on our research findings. I have many people that I need to thank that collaborated on the 4 case studies and experiences that I presented this morning, that I hope you enjoyed hearing about. And most of all, I thank you all for your kind attention. Thank you.
Thank you, Federica. Thank you very much for this interesting presentation. Is there some question, some curiosity or for Federica? Yes, Stefan?
About the hematite formation in the House of the Hunt. Now we have a straight line between the yellow and the red. Is this a result of modern intervention? Because it's not what we would expect for a process induced by heat.
If you're asking if the hematite finding is the result of a modern intervention?
No, not the hematite, but now there's a straight boundary between the two. There's yellow.
Oh, I see.
Partially,
I don't think
horizontal, and the other side it's inclined. But that's with a natural process, you expect something wavy.
Yeah, I agree with you that the line was pretty well-defined. I don't think it's the result of modern intervention. I wasn't the one to work particularly on that case study, but what I was able to gather from my colleagues is that they basically hypothesized the presence of a layer of ash in the lower portion of the room that basically they think might have protected the lower portion of the wall from this phenomenon. And so basically that line that you saw might have corresponded to the layer of ash and pyroclastic material from the eruption of the volcano, just protecting that lower part. And so what you see is the result of the conversion from the yellow ochre to the hematite just happening in the upper portion of the wall.
Yes. Yes?
I'm interested in the Sphinx. I assume that the color was applied through the encaustic technique? Mm-hmm. Wax?
That's right.
Is there a half-life to that technique? Why? It's totally gone after, to the visible eye, after 2600 years. Paintings don't fade that quickly. What is it about the encaustic technique?
I think that was buried under the level of the soil, and that obviously prompted a much more severe degradation that you would expect on wall paintings, for example, or paintings in general,
right.
Just from the burial, from being buried for several decades, centuries, from the burial environment.
Why is there any hint of the color left?
I think that's something that we often observe in artifacts that were buried for some time. Like most of the color is gone, but you would still find some traces that may not be visible under, with the naked eye or even under a microscope, but we demonstrated that, they are there using the analytical techniques. I think it's pretty common to still find even invisible traces.
After another 2,500 years, would it be gone entirely?
Hopefully not, because right now we're displaying the object in a museum under controlled conditions, so hopefully we'll be able to preserve those traces at least.
Thank you. Thank you.
Okay. Thank you very much again, Federica.
Thank you so much for having me. Thank you.